Hi everyone, my name is Yapeng. I'm a PhD student from Purdue University, and today I'm going to be presenting our work DARM, which is disassembling ARM binaries by lightweight superset instruction interpretation and graph modeling. This is journal work of Purdue University and the University of Waterloo. So we know that binary disassembly is a critical first step of many binary analysis tasks, such as vulnerability detection, malware analysis, and binary hardening. However, precise disassembly is highly challenging as a lot of information are lost during compilation. Existing disassembly works usually focus on x86 binaries. Besides x86, there is another popular architecture family, that is ARM. Due to its outstanding performance while using less energy, ARM is widely used in systems such as mobile devices, IoT, and CPS. However, ARM has a number of unique features, making its disassembly different from x86 and bringing a number of unique challenges. The first challenge is, unlike x86 that uses a single instruction set, in ARM, there are two main instruction sets. The 32-bit ARM instruction set is for high performance, and that makes the 16 32-bit sum instructions aim to improve the compiled code density. Here is an example of ARM binary. As ARM and sum instructions are either 2-byte or 4-byte aligned, we list the 2-byte aligned virtual addresses in the first column, and their corresponding row bytes in the hex form in the second column. Its assembly code is highlighted in color. It consists of two code sections, one in ARM and the other in sum, and also an inlined data section. As ARM and sum instructions share the same encoding space, a sequence of 4 bytes usually could be decoded as either one ARM instruction or as one or two sum instructions. Both decoded instruction sequence could look legitimate. This makes ARM disassembly challenging. Besides identifying the instruction boundaries, we also have to decide which instruction set it is. What's more, the two instructions can interwork in the same binary to achieve both high performance and better code density. ARM processor has two execution modes, which is determined by the T bit in a specific register, the current program state register. When it is 0, the processor gets into the ARM mode, executing ARM instructions. And when it is 1, it gets into the sum mode, executing the sum instructions. The mode can be changed by some instructions causing a control flow transfer. For example, the T bit can be set by the least significant bit of a branch target in a branch instruction. In this example, if it is a direct branch and the target destination is 2DC25, as the least significant bit is 1, it will set the T bit as 1. Thus, it branches to the address 2DC24 and also switches to the sum mode. The mode switching is not always explicit. For example, for the indirect control flow transfer, the target destination is unknown. As we said, the instructions in ARM binaries are only 16 or 32 bits long. Thus, immediate values that can be represented in a single instruction have limited range. To deal with this, ARM usually loads a constant from the instruction stream or from the memory and moves to register as an operand. For this case, these cases, it is possible to compute the target destination by interpreting previous code. For example, the MOVW and MOVT instructions set the lower and higher 16-bit of the register R6 separated to make it 2DC25. Then move R1, R5 copies the value of R5 into R1. The store instructions store the value of R6, that is 2DC25, into the target address in R1. Then the load instruction loads the bytes at the address denoted by R5 to R1, which should be 2DC25. Now we know that the target destination of the branch instruction is 2DC25, and it switches to the sum code. We can see that The model switching is highly challenging, and a static analysis can be helpful. Another challenge is that there are usually more inline data in ARM binaries. Inline data is a well-known challenge in disassembly. However, existing works have shown that inline data is rare in x86 binaries, and hence may not that be problematic in practice. However, this is not true in ARM. The statistical results have shown that ARM binaries usually contain more inline data, which may cause a lot of errors in disassembly. In this example, the inline data section is accessed by the load instruction. If we can decide this load instruction is true and also compute the memory address denoted by the value of R6, we can identify the inline data section successfully. As ARM is a RISC architecture, memory access such as load and store instructions are frequently used in ARM binaries, which provide a lot of semantic information. Inspired by this example, our technique is driven by two key insights. First, true instructions should satisfy certain constraints between two instruction sets and also between the instructions and data. For example, an ARM instruction must be followed by another ARM instruction if there is no model switching. And the address accessed by a load or store instruction should be a data region. The second insight is integrating program behaviors can provide rich semantic information, such as indirect control flow transfer and memory access, as discussed in the previous example. This information can provide semantic constraints to help us find more instructions or data. Thus, we propose DARM, a novel technique for ARM binary disassembly. The workflow of DARM is shown in the figure. Given a straight binary, we first use a lightweight static analysis to connect the semantic information and model the binary as a graph. In the graph, we use nodes to denote that the address can be an ARM instruction, a sum instruction, or data. And we use edges and node weights to denote the syntax and the semantic constraints and relations cross laws, which are derived by the static analysis. Finally, the disassembly problem can be reduced to and solved as a problem of finding a subset of nodes in the graph model. We use a part of previous example to show how the graph model is constructed. First, for the nodes in the graph. For each address, we create 3 types of nodes to denote that the address shall be considered as ARM instruction, a sum instruction, and data bytes. For example, the first 4 bytes can be decoded as an ARM instruction, so there is an ARM node. They can also be decoded as 2 sum instructions, so there are 2 sum nodes. It is also possible that they are inline data, so we also have 2 data nodes for these bytes. It is the same for other bytes. Note that if the bytes at this address cannot be decoded as a legal instruction, the corresponding instruction nodes are not needed in the graph. Next, we execute a lightweight static analysis to collect the semantic information, which are denoted as edges. We introduce 2 types of edges denoting 2 types of semantic constraints. First is a conflict edge. A conflict edge is introduced from a node to another node if both cannot be true at the same time. The conflict edges are denoted as dashed undirected edges. For example, if the first 4 bytes are an ARM instruction, then they cannot be sum instructions or data at the same time. Thus, conflict edges are introduced between the ARM node and other sum and data nodes at the same address. The other type is implication edges, which is from a node to another if the former implies the latter. We use solid directed edges to denote implication edges. The implication edges are added for explicit control flow transfer. For example, an ARM instruction must be followed by another ARM instruction if there is no model switching. It is also from the source to the target for implicit control flow transfer. And from an instruction node to a data node, if the instruction accesses the data by a load or store instruction. It is the same for other nodes. For each node, we also count the number of semantic relations in which the node is involved. The more semantic behaviors an instruction has, the more likely it is a true instruction. So we use the number as the weight of the node. Finally, we solve the graph to obtain the disassembly results, that is, to find a subset of nodes in the graph. Actually, the disassembly problem is now a constrained node selection problem. Specifically, each time a node is selected, there are two requirements should be satisfied. First, all the reachable nodes by implication edges should also be selected. Second, all the adjacent nodes by conflict edges must not be selected at the same time. There may be more than one satisfying solution. In this case, the selected nodes with the maximum total weight denote a solution with the richest semantics. To further simplify the selection algorithm, we can replace directed implication edges with undirected conflict edges. And then the problem is reduced to a maximum weight independent set problem, which is a well-studied graph problem. And the existing algorithm can be leveraged to find the optimal solution. In the evaluation, we compare with 6 state-of-the-art disassemblers on different data sets, such as binary compiled with different compilation options, architecture, and instruction set configurations. We also evaluate on real-world binaries and obfuscated binaries. Here, we show partial results compared with 4 famous disassemblers on 3 most challenged data sets. The x-axis is the tool name, and the y-axis is the F1 score. We can see that our tool has stable performance on different data sets and has the highest F1 score among all tools. Our case study also shows that DM can benefit downstream security applications such as binary rewriting. In conclusion, we propose a novel method for unbinary disassembly. It leverages a lightweight static analysis to collect semantic information and models the program as a graph. Then the disassembly problem can be reduced to and solved as a graph theory problem. Our system outperforms state-of-the-art disassemblers. Thanks for listening, and I'm happy to take any questions.
Any questions? Right, I will ask. As you show in the slides, you mentioned you also evaluate this technique against obfuscated program. Can you share more detail about that? What kind of obfuscation technique has been used? How do you get the ground truth?
Actually, first the question for the ground truth actually is kind of different from the x86 binaries. We know that in x86 binaries, it's a kind of a challenge to get the ground truth. However, in ARM binaries, the symbol table contains information called the mapping symbol, which indicate the start address of each section, subsection, and data bytes. So we can get, as we compile all the data sets by ourselves, so we can get the ground truth of the data sets. We only collect this information for getting ground truth, and then we will distribute the binary during the evaluation. And the second question is for the obfuscation, right? For the obfuscation, we add some junk bytes after each branch instruction. So there will be more data bytes in the binary. So we find that for existing disassemblers, it's highly challenging for them to detect these bytes. And for DM, because we consider the semantic information, we can detect these bytes successfully.
So basically, the obfuscation is crafted by yourself.
Actually, it's based on existing work. We should mention that in the paper, and we just modify a little bit to support for ARM binary. Yeah.
Got you. Yeah, thank you.
Thank you.
Any other questions? All right, yes, please.
So I have a question about the analysis. So if it is possible to run the binary in an emulated environment, like QEMU, and so you can collect some
Dynamic information.
If the difficulties comes from you cannot distinguish between the SAMP code and the ARM code, and it's possible to use this dynamic analysis to help you collect more information about.
Yeah. Yeah. Thanks for the question. And I think the idea is possible, but it definitely will bring more challenge because it's not that easy to execute ARM binary in the virtual environment, and also not that in ARM there are multiple architecture and versions. So I think the idea works, but it definitely will bring a lot of more challenges. Yeah.
Right. Let's thank our speaker one more time.